I hope everything is going well with you, sir. Uh,
Yes, I'm doing fine. Actually, I'm on travel, so I'm actually joining from some other place. Okay, so yeah, but everything is good. So I hope you guys are also doing well. Is the placement season on there in BIT Sindri?
Yes, sir.
yes, yes, sir.
So how is it going with chemical engineering?
Sir,
So it
it
is
is going
quite well.
nice.
Okay,
Just few more minutes, sir. Then we will be starting
no
with the
problem, no problem.
webinar.
Take your time. Okay,
Yes. Thank you, sir.
yeah.
Good evening, everyone. I, Diksha, from the Chemical Engineering branch, extend a warm welcome to our esteemed dignitaries, speaker, and our wonderful audience. Today, we gather for an exciting exploration of how machine learning can aid CFD analysis and design in a captivating webinar hosted by Cumika, the Chemical Engineering Society of BIT Sindhi.
Now, get ready to be inspired. I, Ravi, here have the honor of introducing our guest speaker, Dr. Rajesh Ranjan, Assistant Professor at IIT Kanpur. He has done his PhD in fluid dynamics and postdoctoral research, brings depth to his impressive profile.
He worked as a postdoctoral researcher at the Department of Mechanical and Aerospace Engineering at Ohio State University.
He contributed to turbulence modulating while working with industry giants like Boeing, Ferrari, NAL, Suzlon, and Parker Aerospace, making his insights invaluable.
He has also worked on developing turbulence models for predictions in relaminarizing high FPG turbulent flows as a postdoctoral research associate at JNCASR.
Let's take a moment to applaud his expertise, spanning a wide array of specialties. As we look forward to delve into the realm of machine learning and its significance for the future of the industry, I extend a warm virtual welcome to Mr. Rajesh Ranjan. As we are live in YouTube, we also welcome all the YouTube participants to this webinar. Over to you, sir.
Thank you very much, Ravi Shankar and Diksha and the entire Kumika team for this great honor. And it's my privilege to be back here, if not physically, then online. What they did not tell you that I am the alumnus of BIT Sindri, and I did my BTech from chemical engineering, BTech in chemical engineering from BIT Sindri. Okay, long back, and then I switched to fluid dynamics, then high performance computing, and subsequently I went to aerospace engineering. But I have not left the chemical engineering yet, so I will still work in the some areas of the chemical engineering. So today's topic, once again, I welcome you all. And today's topic is many of you might have heard about computational fluid dynamics. Okay, so wherever you talk about flows, whether you are talking about a reactor, whether you want to talk about how the flow happens in a pipeline, or either the heat exchanger, anything to discuss, there are flows, right? So when there is a flow, you want to have a design where those flows can be basically driven efficiently and safely, right? So that's where the computational fluid dynamics come into picture. So what I will do, I will share my presentation, and I will basically start from very basic, assuming that you have not been exposed to CFD. Many of you might not have been. Many of you might have already been taken courses and might be knowing about it. Okay, so let's start from the basics. It may be repetition for some of you, but please bear with me. And I'll come back to the ML part very soon, where I discuss that why CFD requires ML machine learning. Okay, so let's start with the presentation. I'll be switching off my camera to save the bandwidth. Okay, as I'm on travel, and I'll start with my presentation. So how long I have for the presentation? Any idea, Diksha, Ravi?
Sir, you can go with the flow. It's not necessary about the timing. Just
Okay,
you can start with the presentation.
okay, sure. So it will take around like 35 to 45 minutes, so it should be okay, right?
Yes, sir, it is
Okay,
okay.
sir.
It is
No
okay
problem.
with us.
Okay, okay, thank you. Let me share the presentation, and then let me know if you're able to see it. Can you see my presentation?
Yes, sir.
Yes, sir.
Okay, yeah, great then. It's in presentation mode, right?
Okay, sir.
Yes.
Okay, okay, fine. Yes. Okay. So, okay. So, once again, warm welcome to all the audience who has joined with me, with the Krimika team. Okay. So the outline of my talk is I'll discuss about what is CFD, how CFD is useful in the current field that I'm working, that is aerospace engineering, in chemical engineering, how it can help you actually build your career. Because you know many of the companies, I just learned that there's a placement season going on in IIT Kanpur. So many of these companies are looking for the skills, which includes how to perform computation of flows, right? So that's where this chemical fluid dynamics comes into picture. But as soon as you utter the word computational, you need to know a little bit about the computing architecture. For example, whether you are going to use CPU or whether you're going to use GPU, right? You might have heard about this term, graphics computing unit. Okay, earlier it used to be used only for the gaming, but now it is very common to use GPUs for computation. Okay, so then whether you're using the Linux system or Windows system, what kind of coding language you want. So all these things come into picture, and we'll discuss about little bit about how the computing architecture has evolved with time, and how CFD algorithms and schemes have evolved with time. Okay, and then lastly, I will get into why do I need AI and ML. So you might be hearing about these terms like chat GPT, generative AI, okay, deep fake videos, photos, all these things, okay. And you can't be basically blind to it, and you have to basically go with the time and see how we can make use of the state of the art algorithms in improving our CFD simulations, right? So that's where this the third part will come, which is AI, ML, and CFD. Okay, here AI stands for artificial intelligence and ML is machine learning. Okay, so let's start with the very basic. Let's think of it as a lecture, introductory lecture on CFD, and go about that. Okay, so what is CFD? So as the term suggests, CFD is a computational fluid dynamics. Okay, and you want to simulate the flows, or you want to understand the dynamics of the flows with the help of computers. Okay, that's what is CFD means. And I discussed earlier that flows are everywhere. Okay, it can be flows in a gas, it can be flows in a water, it can be in the liquid phase or gaseous phase. It can be multi-phase also. Okay, so wherever there is a flow, you can apply this technique. Okay, so fortunately, uh, physicists have developed the equations which can govern these kind of flows. And now, as an engineer, our job is to ensure that these equations are solved on computer. Okay, and if you can ensure that these equations are solved on computer, then what you're doing is basically computational fluid dynamics. Okay, so this is the very simple definition: the use of computers and numerical methods to solve problems involving fluid flow. It may be fluid flow or the heat transfer, mass transfer. I'm sure you might have taken courses in heat transfer and mass transfer, transport phenomena, fluid flow, fluid dynamics, etc. Chemical reaction, magnetohydrodynamics. You might have combustion, you might have multi-phase flows. So wherever you have flows, you can use CFD. So how do you do that? So we have governing equations, and which are basically the simple governing equations that you see anywhere. There's mass conservation, momentum conservation, energy conservation. These are the main equations. Okay, and depending on the problem, you might have the species conservation. For example, let's say a reaction is taking place. Okay, so you may want to ensure that the species are also conserved during the process. So then there will be more equations. Okay, so the mass conservation is nothing but mass in equal to mass out. In incompressible flow, you can just call it U1 A1 equal to U2 A2. Okay, so that's a very simple incompressible mass conservation equation in 1D flow. Okay, when you have basically 3D flow in the general term, this is del dot U equal to 0 in incompressible flow. So, what I've written here, these belows are basically the compressible flow equation, and you can easily assume the rho to be constant, or basically the total derivative of rho to be constant, d rho by dt equal to 0, and you can go to the incompressible flows. So as a chemical engineer, you would be mostly dealing with incompressible flows, and in that case, the synergy equation will drop out. Okay, the last equation that you see, this will be dropping out. So you'll be dealing with the mass conservation and the momentum conservation. Okay, and depending on the problem, you might have the species conservation, etc. Okay, now how CFD helps, right? So to understand that, let's say we have an idea and we want to materialize it. So what are the things we want to build a product? Okay, and we have a fairly good idea that how it should look like, what should be the purpose of this product, and which segment we're looking at, which market segment that's going to address, right? So what you do, you have a concept and or an idea. Okay, you make a preliminary design based on that, depending on the configuration that is already available in the market. Okay, and from the preliminary design, you go to detailed design where you make a CAD model. Okay, and once you made a CAD model, you will build a prototype. Then you will go for experiments, right? You have experiments lab there, or you might have to go to a special lab where those kind of testing facilities are available. Okay, and then after you do these experiments, you do analysis and see whether it is meeting your objective, right? You might have some idea, some design, but it may be inferior to the original idea that your original design that you have envisaged, right? In that case, if you're not satisfied, you go back to the design again, right? In the process, you vary the parameter. Okay, uh, for example, let's say how the Wright brothers build aeroplane, right? So they had a concept that they want an object which can fly in the air, right? And then they found out, okay, what is a lifting device? That's the wing. Okay, so they worked on designing the wing. What kind of manufacture it should take? What will the weight of that machine? Can it be lifted in the air? Can it give you desired lifting force? What will the drag? All those things. Okay, and then you need some place to where the person is flying is sitting, so that then they had to design a fuselage. Then you should have something to drive the airplane, right? So then there is a power plant, right? It can be a gas turbine engine, it can be a IC engine or anything, right? Then in actually Wright brother did not have the wheels, right? So it was kind of propelled aircraft, right? So what they did at every stage when they made the wing or anything, they had a small wind tunnel. Okay, so they tested the device in the wind tunnel and found out whether it is meeting the requirements or not. If not, they actually changed the design. You know that Wright brothers changed the design many times before they actually flew. Okay, so before that, actually, it failed a couple of times. Right. So they had to go through this process several years before they found that, okay, there is something that is working. Right. So if you are satisfied with the design, with this design cycle, you can go for the manufacturing and you can bring out the product. Right. So as you can see that this process is very lengthy and very, very costly. Every time you have a design, you build a prototype. It's a physical prototype. Go for the experiment or the test in a lab, in a wind tunnel. You may have to go to some specialized labs. Okay, and if you're not satisfied, keep on going through this loop. So it takes a very, very long time, and it takes a very high cost also, right? So during the time of Wright brothers, we did not have the CFD, but now we have, right? So what we can do is that in between this uh, detailed design and prototype experiments, you can put a CFD, right? So what we're doing, we are replacing the physical prototype with a computational model, a model which is there in the computer, right? And as we discussed in the last slide, that we have the uh, basically equations that govern the flow around that object. We can take help of the computer simulations to see how it may be looking like, what could be the performance, right? So you can take that CAD model, okay, do the CFD analysis, see if it is okay, then you release the design, then you go for testing. So the number of experiments have been reduced drastically. So let's say for making one aircraft, you would require hundreds of experiments or test. You might do 90 CFD and only maybe 10 experiment, right? So the cost of CFD is much less than the experiment in most cases. Okay, so in some cases it may be higher also, but in most cases it is much cheaper than the actual physical test. And secondly, it's much faster. And third, it allows you the parametric variation. If you want to do some change in the shape of the design, you can easily do so in your CAD model and run a new simulation without basically building a prototype, right? So if you are not happy with your design, you go do the design modification, go to the CAD model again, and keep on doing this. So this way you can see that how CFD is basically helping you reduce your total design cycle time as well as cost. Okay, I'll just give you one example. Okay, because I am as of now a practicing aerospace engineer. I'll give you one example from design of a wing, but the same thing applies to, let's say, if you want to design heat exchanger, okay, or if you want to design a power plant, or if you want to design a pipeline. Okay, you want to, let's say, transport petroleum or crude oil from some other place to another place, and you want to find out that how do you do it efficiently with minimum losses. You might have heard about the friction factor, how the losses come into picture. So how do you optimally design those kind of system? So same thing applies there also. So let's say this is the wing that I'm designing. Okay, it is inspired by a wing called NASA trapezoidal wing. Okay, so you build a CAD model. So you can see there's a wing here, there is a slat here, there's a flap here. So these are basically the lifting device. Okay, and we want to see how it performs. And this is the 2D view of that. Okay, if you take a section here, somewhere like this is how it will look like. Okay, and then you make a mesh. Okay, so this is the mesh on the surface, let's say on the wing here. Okay, and then you have the mesh around the flap and the slat. So yeah, I forgot to mention, you have to build a computational domain around that, right? So if you want to simulate this body, you have to have a flow coming from, let's say, right to left. Okay, let's say flow is coming from right to left. So you have to make a domain. It's like, let's say, if you want to test a performance of a car, right? So you will put in a wind tunnel and you'll flow an air on top of that, and you see that what is the drag or what are the other forces, right? The same thing, you can think of it as a numerical wind tunnel. You will have a area around that body, and the flow comes into that. And because of that, because of the interference with the body, you will have certain change in the flow, and that's what we are trying to analyze, right? So these kind of things that you see, the mess outside, this is basically the part of the computational domain, which are the fluid domain. Okay, so you might have to give the appropriate boundary condition. Let's say that the flow cannot enter this. Okay, you have to apply a no penetration and no slip boundary condition. The flow cannot slip on this because this is a wall. Okay, and appropriately you have to give boundary condition on top and bottom and left and right, etc. So once you do that, you might have a result. This is from our simulations. Okay, this is basically looks like an oil flow visualization, but this is a computer simulation. So these are, you can see the streamlines which are going around this. You might have a separation here, and once you do the simulation, you will, I mean, after you have sufficient confidence in your design and the simulation, you would like to go with the experiment. So this is the same thing built in the put in the wind tunnel. Okay, same design. Okay, there is a slat, there is a flap, there is a wing, and then you want to do the measurements here, right? So this is what I was saying, that the domain, the tunnel that you see is equivalent. It can be a numerical wind tunnel in your CFD. Okay, and you have to give boundary condition for all these parts. Okay, and once you do that, you will try to compare how your results. So these are the blue ones. You see the results from this wind tunnel, and these are the results from different kind of turbulence models. Okay, so you can see that in some regions the predictions are okay, some regions it is not okay, some turbulence model behave better than other turbulence models. So all these things come into picture then when you start practicing CFD. Okay, you would have to know that there are some flows which are more complex than other. If the flow is laminar, for example, the predictions may be easy, but if the flow is separated, if the flow has got the transition or high turbulence, a lot of rotation, then prediction those kind of flows are difficult, right? So these are the some of the things that we know from a basic fluid dynamics, right? You might have heard about the term called Reynolds number. So if the Reynolds number is high, the flow may become turbulent. In that case, the behavior of the flow is very different from the flow at low Reynolds number when it is laminar. Okay, the flow may become unsteady. It may have certain fluctuations. Okay, so all those key things that you need to keep into account. Okay, so of course you may try to improve the simulations, okay, by changing some parameters, tuning the models of the parameters or the coefficients of the parameters. Okay, and then you, of course, you have to get back to the experiment or the test. There is no escape on that, but it helps you reduce the design cycle. Okay, the time and the effort. So, what is the comparison of CFD versus experiment? So, if you compare the cost, so as we have discussed, it is more economic than experiment in most cases. The time also taken is shorter. You can do the parametric analysis very faster. Once you have established that this code works, okay. The scaling. So let's say that if you want to build, if you want to test Airbus A320, right? So you cannot have a wind tunnel like that. I mean, it's a very big aircraft, right? So then you have to basically build a prototype of the same model which has got every single detail present. Otherwise, it will be a different kind of flow. So those kind of things are a little bit challenging in experiment. But in CFD, you can take the CAD model and you can do any kind of scaling. It's very easy. Okay, all it depends is what is the dynamical parameter, right? For example, what is the Reynolds number, what is the Mach number, what is Prandtl number, etc. Another advantage of CFD is that if you have the grid which is sufficiently resolved, you get the results at every grid point. Okay. On the other hand, experiments, if you, let's say you put probes at every grid point, it will interfere with the flow itself, right? So you cannot basically be putting so many probes or so many tracer particles, okay, in the experiment. So you have results which are very sparse. Okay. So also, like, let's say you want to go and measure what is very the value is very close to the wall, right? For example, you want to measure the skin friction or the Nusselt number or the heat transfer rate, then also it becomes a bit difficult with the experiment, right? CFD, you can repeat it every time. In experiment, it depends. Let's say that yesterday you performed some experiment in Chennai and then there is a cyclone and you want to perform the same experiment, you might get a different value because the climate has changed, the humidity has changed, the temperature has changed, the pressure might have changed, right? So the CFD is not prone to those kind of environmental changes, right? Involved in increases. So safety wise, CFD is safe always, but experiments may be hazardous. You are chemical engineer. You know the most what kind of the hazards that you face when you do some experiment. Okay, you when you want to make some solution or whatever thing you do, you have to basically take care of all the safety precautions. Okay, so those things are not there in CFD. Parametric study is very easy. Okay, effect isolation. This is another very important thing which is very difficult to do in experiment. Right. For example, let's say something is bothering you. Okay. For example, you want to find out you are doing everything correct, but you see that the results are not as per your expectation. Right. So you want to find out. Okay, maybe it is happening due to the viscous effect, or maybe this is how the design is. Right. In CFD, what you can do, you can go to any limit. You can do incompressible, you can do compressible, you can do Euler simulation, which has got no viscosity. You can do basically fully Navier-Stokes simulation where the viscosity and everything, right? So this is what you can do in CFD. In experiments, let's say if I ask you to do a simulation where you ignore the viscosity, you cannot have an air or water where there is no viscosity, right? You don't have an ideal fluid, right? So effect isolation is easy in CFD, but not in experiment. In CFD, you just drop the term which pertains to that kind of effect. Okay, and that is all. You are done, right? Experiments, as I told you, they are intrusive. If you are putting a probe, it is actually interfering with the flow itself, right? There is no problem with CFD like that. The CFT and feasibility, you can always do that. Feasibility in the sense that let's say that you want to launch a rocket. Okay, it's very difficult to measure the temperature of the rocket launch or the kind of speed that rocket is going. So you cannot do experiment on that. So you have to rely on the CFD, right? You cannot do experiment on that. Okay, because of the very high temperature and all, you just cannot perform those experiments, right? The one thing where the experiment is always considered better than CFD is the reliability, right? So as we discussed that we have equation, but then you have to make a sufficiently resolved grid. You have to put appropriate models. You have to put appropriate numerical scheme which are not dissipative, which are not diffusive, and then only you'll get correct result, right? As we saw in one of in the slide here, that the predictions of CFD are poorer or not as expected as you get in experiment, right? So this is something you need to always keep in mind, that when you do CFD, you have to validate against an experimental data before you start using that for the design. Okay. Now let me just give you some example of how where you can use CFD in chemical engineering. For example, if you want to basically design and optimize process chemical processes, for example, a reactor for distillation columns, heat exchangers, etc. You might want to predict the fluid flow, heat transfer, chemical kinetics, combustion, phase change. Anything you do, you can use a CFD kind of tool. Okay, if you want to design chemical plants, the pipelines, equipment, etc. You want to assess what is the environmental impact, because this is a very important topic nowadays, that whatever design or whatever product that you are envisaging, that should have minimal environmental impact, minimal adverse environmental impact. So many companies do this testing, that let's say if you're making a car, how much pollutants are getting out, right? So, and that requires the knowledge of the reaction and all those things, right? So there also you can use CFD. And of course, for the optimization, you might have a design which is going on very well, but then there's a lot of market competition. So you want to optimize the design time to time, right? You want to improve your design. So, and you want to make it more safe or more efficient. So in those cases, CFD is very, very useful. Okay. So these are some of the examples. For example, this is a reactor, heat exchanger. This is a plant. Okay, where you can see, for example, you want to see that the emittance is coming out here, where they are going and how they are spreading. So you can do this kind of simulation here. Inside the heat exchanger also you can do simulation. You can find out, so for example, you can see the red zone and the blue zone. So they may indicate whether the mixing is which side the mixing is higher, which side the mixing is lower, so on and so forth, or where the stress is higher and stress is lower. Okay, but having said all these things, the fluid flows are complex. Okay, so it's not easy to basically do CFD unless you do it very very carefully and you have the right resources and right tools for it. If you look at this picture, for example, so this is a flow which is laminar, right? So if you want to simulate it, this is not changing with time. There are not undulations in this flow, so this may be easy to simulate. On the other hand, if you go to these kind of flows, first of all, there are multiple scales. Okay, these are the turbulent flows. So turbulent flows are considered to be the scales which can be in a variety of range. For example, you can have something which is order of millimeter, and something it can be order of like meter, right, or kilometer. If you, let's say, if you want to simulate the climate, right, let's say you want to see that how the earth gets hot and how it rains, or how it gets vaporized and it rains, right? So the system that you're considering is from earth to very high in the atmosphere. Okay, so you have a scale which is very close to the earth, how the temperature is changing there, and you have a scale which is going all the way maybe to the stratosphere, right? So this kind of flows have got very large scale. Okay, you can have something in nanometer, right? But in order to understand the effect of nanometer, you have to go to a scale which is of meter. So the range of scale is 10.9. So that means you should have a grid which is capturing both the nanometer and both the meter, right? Nanometer and meter. So because of these variations in the scale, simulating turbulent flows are generally harder. Okay, and then in between you can have transition. Okay, so the laminar flow may become transitional and ultimately it becomes turbulent. Okay, so transition is in between laminar and turbulent. So that's a topic for a different day. I don't want to delve into that. Okay, but solving these transitional flows are also very, very challenging. So depending on the problem, you want to choose an approach which can give you one or the result. For example, if you're using a model-based simulation, which is typically called Reynolds average Navier-Stokes France. So you're getting a flow like this. This is nothing but the mean flow. Okay, this is just the average of the flow. So let's say if you are doing some experiment and the flow is turbulent, and what you're doing is you are capturing the snapshot every time. Let's say you captured it for 1,000 times, and now you average it out. Okay, and how will the snapshot look like? That is what is the range here. Okay, it's an average flow. It is always an average flow. It cannot give you the instantaneous variation in the flow. Okay, better than that, if you want to get the instantaneous variation, is the LES. You can see that you can see some of the undulations here. Okay, there are some scales, this scale, and then longer is this scale, like this, right? So this is called large eddy simulation, and this is called the direct numerical simulation. All are same flow. Okay, and you can see the variation in the scale, right? There are scales like very small, and the scales which are very very big, right? So as you might have guessed, that simulating the DNS is the hardest, because your grid should be able to resolve this small thing also and the big thing also. Okay, so these are called the eddies. Okay, in turbulent flow system, in fluid dynamics system. Okay, so for DNS you require basically a very high computation. So you can see this computation cost is increasing as you go from RANs to DNS. You have intermediate approaches, also hybrid approach like hybrid RANs, LES, URANs, which is not shown on the right. But overall, the picture is that if you are using a modeling, then the computational cost will be lower. But at the same time, the fluid flow simulator will be simpler. Okay, it might not capture all the complexity in the flow, but you might want to go through direct numerical simulation where there is no model, but the cost of the computation is very very high. It is like order of several orders of magnitude higher than the RAN simulation. So if you're working in a company, your job is to make a balance between the two. Right. If you are doing RANs, you're getting an average picture, but it might not be capturing some critical flows. theoretical features of the flows. Or if you're doing DNS, it is too expensive to do the simulation. Your manager will not allow you to have this kind of computational time because that involves a lot of cost, right? So how do you make a balance between the two? You might want to go to LES or hybrid approach or URANs, or you might want to improve your turbulence model to basically get the same flow feature. So that will come with the practice, right? So a good CFD practice requires a good strategy. It means that what kind of numerical schemes you're using, what kind of discretization, whether it is finite difference, finite volume, finite element. Okay, in the schemes, whether it is dissipative or diffusive, or it is giving a very accurate result, all these things come to picture. Okay, and finally, whether the flow is converging. You have to show the grid convergence in the sense that the solution is not changing if you are changing the grid, right? And all the numerical convergence, that all the equations, let's say you are satisfying the mass conservation or the momentum conservation, so they are satisfied to the good precision level. Okay, let's say 10 per minus 6 or 10 per minus 7, etc. But all these things require a sufficient computational power, right? So if you do not have good computational power, you might have good strategy and schemes and discretization scheme, etc. But you will not be able to simulate the flow, right? So that's where I'm coming into the second part of the my topic, which is how computing has evolved versus CFD. So how good I'm doing in terms of time? Just let me ask this question. Okay, so I have already spent around half an hour. Okay, so this part I'll be a little bit fast. Uh, so may require another half an hour if that is okay with the organizers. Okay, so uh, is that fine?
Yes, sir. Yes, sir.
Okay, okay, fine. Okay, so as I told you in the very beginning, that if you want to do CFD, you need to know a little bit about the computing architecture. You cannot be blind about what is going in the world, how the game in computing is changing. Right, you have to be aware of that to be a good CFD engineer, okay, or a CFD scientist. Right, so let's discuss a little bit about the computing architecture. Let's change the gear here. Till now, we discussed about the technical part of CFD. Now, I'll be discussing the technicalities of the evolution of the computing architecture. Right. So, those who have some background in computer science, they might be aware of this law called Moore's law. Okay, what it says is that the number of transistors is basically it gets doubled every 2 years, right? And as you know that the transistors are what is making your computing faster, right? So starting with a few thousand transistors in 1970, now we have around billion transistors in one single chip. You can have billion transistors which are fit in your motherboard. Okay, you can see around 2020 it goes around to the some billion transistor, right? So the Moore's law is okay, it is increasing, and you have seen it has actually followed the law very well, but now it is getting saturated. And why is that? Is there are two things here. One is that if you want to fit in a more number of transistors in the same chip, it comes with a cost. You need to basically cool them, right? So if you uh, try cooling them, it will basically not give you the effective benefit that you want, right? So that's one thing. And uh, so, so that is related to two things. One is that the heat, and the same thing relating to the power consumption. So that's why they have basically change this idea of including the number of transistor because it has got saturated, and they have gone into the different paths of the computing architecture itself. Okay, so what are those paths? Let's go into that. Okay, so this was a statement made sometime back around 2010 that if you want, you could build a exascale computer today, but you might need a nuclear reactor to power it because the requirements of the cooling is as such, right? If you go with just doubling the number of transistors. Okay, so this is again another view of how the transistor has saturated, the number of transistors has saturated. Okay, after around 10 to the power 8 or so. Okay, The thread performance also saturated. The clock frequency, as you know, that how many. Uh, so every computer has a clock. Okay, you might have heard this term 2.1 gigahertz and 1.8 gigahertz and so on and so forth, which indicates that it is synchronizes the operations during that time, right? So let's say you have some floating point operations per second, but it has to be synchronized with the clock speed, right? So the clock speed, if it is increasing, that also means that it is becoming faster. But you might see that initially it was a lot of increase, but recently there was some decrease as well. Okay, and what is the reason behind that? We went with the approach of multi-cores, right? So around 2005 or so, you would see that the number of cores in one computer started increasing. For example, you might be using a laptop or a desktop which has got quad core or basically octa core. You got 8 cores in one number of uh, uh, processor, right? So earlier it was always one core, so people actually invested time in increasing the frequency. But now with the number of cores increasing and to balance with the cooling requirement, the frequency has been decreased. But then you can basically use the parallel computing power. Okay, and the power is also kind of saturated here. The other thing that maybe of interest to you is like, for example, the computer memory and storage. So if you want to buy, you would have wanted to buy, let's say, the memory of uh, 1 TB, 1 TB of RAM. In 1956, it would have costed you $100 trillion US dollar, right? What you can do nowadays, around 2022, it may be around $5,000. That's all, right? So the cost of memory is decreased drastically, and so is the cost of the hard disk, right? So what would have costed you $10 billion, now you can have like just $100. You pay 10,000 rupees and you'll get a hard disk of 4 TB maybe, right? So this was not envisaged at that point of time. That means we can afford to do high computation where it can take a very big grid and you can store a very large computational data nowadays. Okay. So what is the future of computing? So one thing I forgot to mention, that all this number of transistors that you are talking about, it follows an architecture called complex instruction set computer, CISC computer. Okay, so it basically worked on the principle that you don't have to give too many instructions for simple operation, and just give one. Let's say you want to add a plus b, just write a plus b and it will do the thing, right? So in response to that, there was this RASC was developed, which is called reduced instruction set computer, or also called ARM, which is advanced risk machine. Okay, so what it does is that instead of using the complex instruction, it basically made the instructions simpler, but many instructions for a single operation. Let's say if you want to do a plus b here, then what you do, you first assign a, then assign b, then do a plus b, and then again that give me a plus b, right? So what was done in one instruction in CISC, not it requires 4 instructions. But because of this reduced instruction, the heat consumption got down and the power consumption also got down. So you might have read about this M1 and M2 chips, which is manufactured by Apple for the Mac machines. So they follow this RISC architecture. Okay, it started with the mobile phones, but now it is part of the computers also, and it is evolving, and now it is getting into HPC also. This kind of architecture. Okay, the second thing is the accelerator. So as I have been discussing, that uh, we have changed the game from CPU to GPU and many integrated code processor. So GPUs, as you know, they have got many more number of threads than the CPUs, right? So you can utilize those threads for your parallel computation, and that's where the GPU come into picture. So they can be used as an accelerator, or nowadays you can independently basically do the communication and everything on GPUs and make your code very fast. Okay, but there's a catch. You need to write in their own, in their language. Okay, you might have to use CUDA, which is a language followed by NVIDIA GPUs, or you might have to use some kind of accelerator. Let's say OpenACC is one accelerator. Okay, or there's a HIP. Okay, which is also used for GPU computing on AMD devices. The third is heterogeneity. So basically, you have the computer which is completely hybrid. You have something GPU, something CPU. Some are basically the RAMs also have basically the heap size. Okay, I'm using too many computer science jargons, but maybe you, when you go back and see, you'll probably know. Okay, so the cache size is higher, the heap size is higher. You have different kind of RAMs installed. Some are DRAMs, some are installed in the GPU card itself. Okay, so all those kind of heterogeneity is possible, and that's why where we are heading into. Okay, and the last one is basically the quantum computing, which is the talk of the town. Okay, so you will be solving everything in terms of quantum variables. Okay, and it has got certain advantage. Okay, and it looks very promising, although we have limited success as of now. Okay, so IBM has built the system one, but they have also built the system two, and the algorithms are being developed, which can be used if a quantum computer becomes available in the future. Okay, at a reasonable cost and good performance. Okay, so okay, I'll be skipping this slide. It's just show that how the GPUs will evolve. Okay, from 99, which is GU4256, which is being used for gaming. Now we have Ampere A100. Okay, and from like very few gigaflop, it is like one A100 can give you around 20 teraflop of performance, right? Compare with your single CPU, which is like maybe 100 time less than this performance, right? So one GPU can basically give you, so flop is floating point operations per second, right? So if floating point operation may be addition or multiplication or anything, so it can do these many teraflops, these many operations in 1 second. Okay, so and you can also see that the L2 capacity. So L2 is something which is very, very important for efficient computing. Okay, efficient and fast computing. So earlier what was like 1 MB, 2 MB, now we are discussing about 40 MB of L2 cache. So there have been revolutionary changes in terms of how we look at the computing from 19, let's say 99 to 2020, right? So can we make use of those evolutions or the performance benefits in computing in our CFD? Have you made use of that? Unfortunately, no. The reason for that is the algorithms are still the the old ones which were developed in 1950s or 60s. There has not been much change uh, the computing algorithms, right? And this is one of the reports by NASA, which talks about like what we can do in CFD for next, let's say, 30 years or next 20 years. So this was released in 2014, and it's called NASA Vision 2030. Okay, and they found, for example, if you look at here, they found that when the flow is separated, it's very difficult to predict the flow using so they made a machine called decision gate that if it, so let's say by 2018, if it does not work, then maybe you have to go to hybrid RANs LES, right? So if it is no, then it go here, right? And which is very much more expensive than the RANs model. Okay, and for not developing good algorithms in CFD compared to the evolution in the computer science is because of the lack of investment in these areas. Computer science is a very I don't know is a field which gives you good return on investment. Okay, so that's why there have been a lot of investments there, a lot of companies which have come out. Okay, starting from NVIDIA to like AMD and so many other companies competing with each other and getting new and new architectures every year, right? But in terms of simulation strategies, these are basically limited to the academic people, which does not have that much of funding or investment. So we have resulted in stagnant simulation capabilities, right? So again, look at here where they've said that you can't use ranch models for the CFD simulation when the flow is complex. For example, when it is the flow separation, etc. Right. I'll get back to this again. Okay. Let's go to the third part of AI ML in CFD. Okay. And I'll connect it to the first two parts that we've already discussed. First is the CFD, second is the computing architecture, and how we can use both these things to improve our CFD predictions. Now, what is AI/ML? So AI is basically it's a larger set which includes like anything that mimics our human intelligence. So you have a natural intelligence. If you can design a system which can mimic that natural intelligence, then it will be called as artificial intelligence. And we are coming very close to it with generative AI approaches like ChatGPT, etc., where it can generate the design or generate the text or generate material which is not it has not seen earlier. Okay, so we are coming, although I mean if you want to, let's say, compare with the brain, right? So the number of neurons that we have brains, like billions of neurons in the brains. Okay, compared to that, if you look at a neural network in any deep learning algorithm, that's nothing. Okay, so we have a long way to go, but we are getting towards there. So artificial intelligence is the highest set. Within that, machine learning is one tool which can basically give you the artificial intelligence, and that involves basically algorithms like gradient descent, etc. Okay, some kind of optimizer. Okay, to make the predictions better from the data. And a subset of machine learning is the deep learning, where you try to mimic our brain by putting some artificial neural network. Okay, and here's a diagram of how the field is changing. The deep neural network is now a very, very hot topic. So how does it relate to the development in computing, right? So all the core algorithms, for example, the deep neural network and convolution network, back propagation, stochastic gradient descent, etc., they were all developed in 1980s, okay, by people in mathematics and computer science, etc. But they were not usable. They were not able to efficiently use it until very recently. Okay, why is that? Because we did not have powerful enough hardware, right? If you don't have a powerful enough hardware, even if you have the algorithm, you cannot make use of that. So that's what I said in the towards the end of my first topic, that you might have a CFD algorithm which is very good, but if you don't have a sufficiently powerful computer, then it is of no use. So something happened in ML, etc., where these hard algorithms, we did not have a good powerful network to train those data. Okay, but arrival of GPUs, when the GPUs came, it changed the game, because as we have discussed, it can give you 20 teraflops, 100 teraflops, etc., in one box, right? So that means you can take a more complex system, you can train it and make it for our some of the algorithms which have been developed for our neural network. Okay, so let's start with the. I'll not go into ANN and CNN, okay, because I don't have time. I'll directly start with the deep neural network, okay, which is the part of deep learning. So what happens? I mean, to think of very simply, that we have a function y, we have the output y, which depends on x1 and x2. Okay, what the network does, so this is our network, it takes this input x1 and it tries to fit in the data so that it gives you y. You can think of a very simple system, let's say linear system. You have x1 y1 and x2 y2. You can put a line there and you can make equation there. A simple, very simple example, but then it can be quadratic and can be anything. So that's where it comes into uh, uh, these weights and biases. So W1, W2 are weights associated with these input variables. Okay, and then B is the bias, and F is the activation function. So you can use x1 W1 plus x2 W2 plus bias and so on and so forth, and this will be at every neuron, and then you use a function, and that should be satisfied, and if it should give to y. Okay, So the kind of activation function you may have sigmoid, 10H, rectified linear unit, and there are many more which are coming nowadays. Okay. So in the this is a simple network, okay, simple artificial neural network, and this is the network where you have between the input and output you have several layers. Okay, so several weights and biases, and then several layers. So you can have one layer, two layer, and so on and so forth, right? You can have 10 different layers. What it does is that if your function is more complex, it cannot be solved in one layer. For example, if you think about Navier-Stokes equation, they are basically spatio-temporal partial differential equations. Okay, these are very, very complex. Depends on the space variable and the time variable and so on and so forth. So you cannot use a very simple addition. You can map to use very large number of layers, right? So, so this also is there for a very long time, but this was not used for CFD. There are 2-3 reasons. One is that it requires a lot of training data. Usually, when you talk about deep learning or machine learning, you think about data because data is required to train that. How do you go from x1, x2, x3, x4 to y1, y2? Right? You use a lot of training data, and so that it gives you because there is no physics behind that, right? So when you say mass conservation, you have some physics in mind that okay, mass in is equal to mass out, right? When you say mass conservation, it's a momentum in is equal to momentum out. The same is not true with the deep network. Into physics, right? It totally works on fitting the data for a given input to a given output, right? So that was the problem. And for the same reason that you don't train it for something and this network will not understand, right? So what is the way out? How to basically do it better? Is that put physics into data, right? So you for the given input, you got the output UV, for example. These are my neural network, and you got this output. Now what you want to do is that you try to satisfy your Navier-Stokes equation using UNP here, see whether it is going to satisfy your mass conservation, amount of conservation or not. If you can do that, so you take this UV, okay, for a given XYT, get UV, use your mass conservation, amount of conservation, and see if it is not going to zero, then find out the loss. Okay, put it back there, use the back propagation. That means that you tell the network that okay, I'm not still getting zero, my conservation is not yet satisfied. Please change your weights and biases. And how will it change weights and biases? By stochastic gradient approach, that it will see which side, if it moves, it is getting better, and it will start moving that side. Okay, so all these things are inbuilt. So you can have loss which is due to the data, and you can have loss which is due to the physics also, right? And now we have put physics into data. The this physics from the network. So this is called the new area. So this is what I spoke. You can take the name of class. This is the algorithm. I will not go into detail. I'll just give you some example. Okay. So this is, for example, a flow over a lead-driven cavity. What is the problem here? That the top one is this is not an inlet. This is basically a typo. It's a moving lead. Okay. So the lead is moving on the right, and when the lead is moving on the right, there will be a flow which is getting developed here. Okay. And this is a very common problem even in chemical engineering. When you start doing your CFD, this is the first problem, one of the first problems that we solve. This is called flow that I'm showing. Okay. And one of the advantage of this spin approach is that you don't need a grid. You just basically distribute your residual points in the body. Okay. You have to put some more points on the boundaries. Okay. And then you just try using the network. allocation points on the domain, 3D players. Okay, on the boundaries also you have to put the points because you need to certify the boundary condition also. Okay, and then some of these things, what kind of optimizer you're using, the learning rate, okay, all these things. I'll not go into the details there. And then you do the basically the network prediction, and you see whether our loss is coming below certain value or not. So what is this loss here? This is loss is you can think of as a residue in your CFD simulation, that whether my mass conservation or momentum conservation is getting satisfied or not. If it is not set, if it is set, so when it goes 10 by -4, that means that my physics, my the loss, my physics loss is minimized. That I'm satisfying the conservation equations sufficiently well. At the same time, also satisfying the boundary condition. Okay, so the loss, as I told you here, it can be the physics loss, one PD loss, which is the conservation equations, the boundary condition loss, whether it is satisfying the no slip etc or not, whether it is satisfying that the initial condition loss also. Okay, so if it is satisfied, and these are some of the results that you can see that result. The line is from pin, and this red one is from the CFD simulation, and you can see that it is predicting it very well. Okay, here CPU runtime is very small compared to the CPU runtime. Okay, so it's around 16 times faster than CPU. And this is again the difference between CFD and pin. Okay, and you can see that the difference is very minimal. Okay, only towards the corner there are some differences, otherwise both look very similar. Similarly, we have done the flow past a cylinder. Okay, again it's a laminar flow, and you can see that the CFD and pin predictions are on dot. Okay, and these are different losses that I was talking about. This is the boundary condition loss, the yellow one, the red one is Y momentum, the blue one, green one are the Y momentum and continuity, etc. And you can see the spin on the left and CFD on the right, and quantitatively also it matches very well. Okay. Similarly, we have tried for aerofoil. So again, I want to tell you that this is an evolving field. Okay, we are still trying very simple simulation to see if the neural network is able to give you the correct predictions or not. Okay, these things are very simple in CFD, but we are trying to make use of the neural network to basically do the CFD kind of get a CFD kind of capability. Okay, so this is again on aerofoil. The one thing I want to speak about is the turbulence modeling. So I remember I've shown you a flow where the flow was turbulent, and I discussed there were a lot of scales. And if you want to solve those flows, either you have to do DNS or you do some kind of RANS model. RANS model is what? It basically models the turbulent scales. So it has additional equations. For example, you may have K epsilon model. You may have so that will have K equation and epsilon equation. This is the turbulence kinetic energy, and this is the dissipation rate. And then you try to satisfy these equations. Okay, the K equation and epsilon equation. If it is satisfied, then you can use this parameter based on that neural network, and you can see that the pin and the top one is the DNS, and this is the default range. And you can see the pin prediction is better than the default range. Right? Why? Because we have predicted the value of the parameters in the model correctly using the neural network. So these are the values which are used by different literature, and these are predicted by the pin. So pin can be used for anything. Okay, I'll just give you an example for the chemical engineering students. So let's say you want to find out whether equations are stiff. That means the some equations, some reactions are happening at a very fast speed, and some equations is happening at a very slow speed. Right. So you might be knowing that when there's a lot of disparity between the two, then solving those kind of kinetics are not easy, right? Because again, there's a scale problem. You have to work with both the highest scale and the lowest scale, right? So we can use the CFD prediction. Let's say there are three equations there, okay, and we use the pin. Okay, so we are trying to satisfy these equations here: initial condition loss, residual loss, and you can see that the predictions of the pin is on dot. Although you can see that there are two pin here. One is a regular pin and the other stiff pin. Okay, regular pin, there is prediction is not that good. The green ones, Okay, but the stiff mean gives you very good predictions for all three reactions. Okay, so again, there are several approaches of pin which is getting popular now. One is weighted pin, other is as you are seeing stiff pin. Then there are pins with multiple domains. Okay, so because it's an evolving area, there's a lot of scope of how you can use this approach to solve your problem. And these are the evolving things which you can use. For example, here you can see there's a GitHub database also where you can directly use to see how the predictions are coming. Okay, so last couple of slides. Okay, I've already taken more than 1 hour. So there are issues. Okay, it's not like that. If you use neural network, it will replace your CFD and with that. Okay. For example, there are issues of repeatability. It is highly dependent on what kind of initial condition you have. Okay. Every time you change the initial condition, your results change, right? So there are ways to get into that. One is that you can use transfer learning. That means the results from one simulation or one neural network can be used for the next prediction. Okay. The other is that you use training data along with the equation. So you satisfy the mass conservation, momentum conservation, but also use some data. So it will satisfy the PD loss, the boundary condition loss, initial condition loss, as well as the data loss. Okay. So then it will become better with time. Okay. The cost as of now it is higher than CFD, but that's why it comes to picture that it should not replace CFD, but rather it should aid CFD. So for example, I was discussing that in turbulent predictions, CFD was not doing good, but we used PIN, got the calibrated model parameters, and we got a good prediction, right? There are issues in extending to 3D flows because, as I told, it's very, very expensive, but that it can be used for turbulence modeling. And do, let's say, if you need the grid size to know that simulation is getting better, right? In most cases. Same thing is not true in or anything. If you increase does not mean it is a convergence of your process. It may give a completely different result, right? So we have to basically work on that to see how it becomes more consistent, more and more unique. Okay? Better model scope, it can solve inverse problem. In the sense, you can train it from left to right, but now once it's trained, you can use from right to left. Okay, so given the value of the velocity field, how do I get my the equations, or how do I get my original database, right? Uh, because this can also be used for optimization. Let's say some design, you did the file, fit it, and found that this is the CSV different drive. So use the inverse problem, change the surface, they change. To the experiment, and you know that in some location you cannot get the data because of the limitation of the equipment. You could put stone near the wall, you cannot put a data. In some location, if it is outside your body, uh, and yes, they remove the decision gate. They devised this database vision document in 2020, and they said that okay, if you can use machine learning, probably it can make the surveillance models better, right? So that's how the neural network can be useful in your CFD simulation. Okay, so this is the last slide. Okay, so the question is, can machine learning replace the traditional CFD? In my opinion, no, and that is not the purpose either. But it can augment. It can make the CFD simulations predictions better. It can probably enhance the capability of the CFD. As I told, the RAS models can become better. Okay, and yeah, it can make the predictions faster also. The models can become better. You can see that these are the publications in this area, which is increasing exponentially. And with that, I would like to thank you. These are some of my contributors. Okay, from my gurus to my collaborators, students, etc. So yeah, I understand it was a very long talk, but I hope it was useful. Okay, and I'll be happy to take questions if any. Okay.
Thank you for the preview of what lies ahead. We are elated to gain insights from your remarkable journey, and your knowledge holds immense significance for us. Your invaluable insights have made a lasting impression, and we express sincere gratitude for the wisdom you have shared.
That's the approach we take. We invite our audience to post questions or share their thoughts. Feel free to type your questions in the chat and we will address them shortly. Okay, sir. So there is the first question from one of our viewers. It is, as students interested in this intersection, what resources or learning pathways would you recommend to deepen our understanding or both CFD fundamentals and machine learning techniques?
Yeah. So my suggestion is that at least take like one. You might have already taken numerical methods course. Okay, you know, like how to solve like using bisexual method, or how to march in time using Runge-Kutta method, right? So that you might have already heard. So what you can do, that you can start solving simple equations like linear convection equation, non-linear convection equation, okay, or heat equation, wave equation, etc. So once you're able to solve that, you can probably increase the complexity slowly, go to one-dimensional Euler's equation, then one-dimensional Navier-Stokes, then you increase the dimensionality. Okay, there are several tools available nowadays. You can use OpenFOAM, for example, for your CFD simulations, and the learning curve nowadays is not very big. But what I emphasize that you should have good hold on the fundamentals, right? So it will be a good idea to have a course in CFD, at least a basic level course where you understand what is going on. Some schemes work, some schemes do not work. They blow up. Some schemes are good for hyperbolic flows, some are good for elliptic flows. So those things will know where if you take a good course. There are lectures on NPTEL. Okay, there are lectures on Coursera. Your institute may also have some structure course. So please take that. So and try practicing. So there is no basically alternative to getting your hands dirty. You have to start solving simple problems. Okay, as I discussed, lid driven cavity, flow passer cylinder, etc. You can start solving using, let's say, OpenFOAM. This is for CFD. For machine learning, the first ingredient I think that you must know is the Python language. Okay, so that is essential because of most of the libraries that you see in machine learning are written in Python. So once you know Python, you start investing a little bit on PyTorch. Okay, so the PyTorch is I think it's one of the most I mean efficient tool for writing your machine learning codes, and write simple networks. Okay, learn the importance of, or learn the basics of what kind of optimizer you can use, what kind of like gradient descent algorithms you can use, and slowly this is how you build it. And once you learn those things separately, then you can start thinking of integrating the CFD and ML. Okay, so I hope this, and there are some tools. For example, if you're using NVIDIA GPUs, you have a tool called Modulus. Okay, that has got like pin what I was talking was already implemented. Okay, they have given some examples online also. or there are open source tools like DeepXD. Okay, that's also you can use for training your network. Okay, so there are a lot of examples available nowadays. Go to GitHub, lot of codes will be available. So start getting your hands dirty, and slowly, when you get interested, take some courses, and this is how you will develop your interest and your skills.
There are
Yes,
some
back
more
to Diksha.
questions
Yes, Ravi,
like
tell me.
how do you foresee the future evolution of machine learning techniques in the context of CFD? And what advancements can we expect in the coming years?
Yeah, so I mean, as I've emphasized through the presentation, is that see we are basically going through a significant change in the computing power. So we might be getting into quantum computing say maybe 5 to 10 years, right? So there these algorithms may become even faster, right? So that's one thing. Secondly, the CFD models will become more and more accurate with time. Okay, because it will learn from the data, and the databases are there, and also as we are satisfying the equations also. So it is now basically we have the benefits, the best of the both, right? You have the experimental data or the high fidelity summation data like DNS, and as we have the governing equations. So we are making the best use of that to make our predictions. So some of the situations, for example, if you want to do a high lift aircraft simulation, which is a very complex simulation, it's still not possible with CFD. So I think in future it should become possible to do these simulations. Also flows like which has got large separation or transition or reluminization. So those kind of flows which are currently not predicted by most advanced models may become possible in the future that we can predict those flows.
So we have another question here. How can students contribute to ongoing research in this field, and what opportunities exist for them to apply their knowledge in real world scenarios?
Could you please repeat your question because there were some network issues here?
Okay, sir. The question was, how can students contribute to ongoing research in this field, and what opportunities exist for them to apply their knowledge in real world scenarios?
Oh, the law opportunities are limitless. Okay, I mean, what we talk today is the state of the art. Okay, it's not like what we're talking, what happened 10 years ago or 5 years ago. Today is the state of the art. Okay, so any design process. Okay, I mean, starting from chemical engineering to mechanical to aerospace, the tools that you will be learning can be used for optimizing your design. Okay, so anything that you're designing can be better designed using these tools. Okay, so there are no dearth of opportunities. And in fact, if you, I mean, most of this industry, including the automobile industries or chemical industry, they started using this AI ML in their design process. Okay, so if you are into that, you are basically one of the front runner who can contribute to this field.
Another question, sir, is where CFD is underutilized but has a great potential for transformative impact.
Um, I think it's difficult to answer that question. Uh, but I think, see, many of the industries in India, they rely more on experimental database, right? For example, you see ISRO. I mean, they have actually very good experimental facilities, and they have made their most of the designs mostly relying on experimental database until very recently, until maybe 20 years back or so. Okay, but now they started using CFD. Okay, so I mean, Indians generally were very good users, very good experimentalists, right? So what I am proposing is that the CFD
can probably make a difference and reduce the design cycle by a lot. Okay, and we should make use of that. But I think it also depends on what kind of industry you are getting into. Okay, uh, the leadership which is running the industry may have confidence in something and others may have confidence in other things. Okay, so in commercial softwares, most of these industries rely on the commercial softwares, and they have got their own limitations. For example, if you're using S Pen or Fluent or Star CD, okay, so they may be working or they may be designed, or console for example may be designed for a particular flow which where it is giving you excellent result, but in some flows it might not be right. So there you require a very in a fluid flow simulation.
Okay, sir.
Yeah.
So here we have our last question. In the broader context of engineering, what are the key benefits of incorporating CFD simulations into the design and analysis process?
Two things. Okay, one is that your price, another is cost. Okay, so the price, because as we discussed very early, that if you want to design anything, you have to go through the design cycle. Okay, from the preliminary design to detailed design to CAD model to prototype building to do the testing, analysis. If you're satisfied, then go proceed with the design, and then if you're not satisfied, you go back. Usually, is a this cycle is very long. Okay, you may have to like you may make hundreds of designs and choose one of them, right? So that means you have to do hundreds of experiments, hundreds of prototypes you need to build. So it will cost you a lot, and it will also take a long time. It may take 5 to 10 years to get design out, right? You can accelerate this process by using CFD. Okay, by basically in between designs and prototype, or some change in the parameters that you want to do in your design, you can easily do with CFD. And then once you are confident that okay, this design makes sense, then compare with your CFD, right? So for that you should have a good CFD solver, and you should have a good CFD group which understands what is the basic difference in the flow and the model solve the problem. That means there will be more team. Okay, that way both these things and you can make it easy.
Thank you, sir, for this session. It is my distinct privilege to invite our respected faculty, Mrs. Seema Pandey, ma'am, to share her insights on CFD simulation. Over to you, ma'am.
Thank you very much, the Kumika team, and I'm very much honored. Okay, as I've been telling that it has been a pleasure, and I really appreciate all your efforts in organizing this event and for this token of love. I'm really grateful. Thank you very much.
Thank you, sir. Thanks to our professor and participants for joining us and actively engaging us. Your cooperation is greatly appreciated. We hope the knowledge shared today will kindle your curiosity and inspire machine learning. Thank you, and may you have a wonderful day ahead.